Today we are presenting our analysis of the Big Stream Fire Operations case. Our goal was to build an optimization model that determines the most efficient firefighter staffing schedule while still meeting all required coverage levels. Our team consists of Nathan Garcia, myself, Brendan Koh, and Samantha Lee, and we are all business administration majors. Together we built a model, tested different staffing scenarios, and analyzed the results. In this project, we built an optimization model using Excel Solver to minimize total staffing costs while meeting all firefighter coverage requirements. We created a base model and then tested different scenarios to evaluate how staffing decisions affect cost and efficiency. The goal of this analysis was to develop a scheduling approach that maintains enough firefighters on duty while minimizing personnel costs. Efficient scheduling helps reduce unnecessary labor expenses while still maintaining emergency response readiness. The case focuses on a staffing challenge faced by the mayor of Big Stream, a town with about 75,000 residents. The mayor must balance maintaining enough firefighter coverage for public safety while also managing staffing costs efficiently. The current scheduling system has two 12-hour shifts, a day shift from 5 a.m. to 5 p.m. and a night shift from 5 p.m. to 5 a.m. Firefighters work 4 consecutive shifts followed by 3 days off, and each shift includes a base pay plus a 33% benefit cost. Now that we understand the current scheduling system, Nathan will walk us through the base model and the results.
To begin our analysis, we developed a base optimization model to determine the minimum cost staffing schedule while meeting all the firefighters' night and days coverage levels. Our results show that the current schedule costs about $157,046 per week and requires a large number of shift assignments. Although this schedule ensures public safety, the model reveals inefficiencies such as excess staffing during certain periods. The base case establishes the problem we aim to improve, which is how do we reduce costs while maintaining emergency readiness. We examine how increasing night shift staffing requirements affects the total labor costs. In the one-person weekday night scenario, there is no additional cost because the schedule already had excess night staff. When the requirements increase beyond this surplus, such as 8 additional weekday night shifts, the cost rises to $6,384. When the 4 additional week and night shifts are required, the total cost increased to $3,192. When 3 people is added to the weekday night shift, it increases to $9,576. This slide presents a detailed example where only 1 additional firefighter is required during the weekday nights. Compared to the base case, the staffing requirement increased slightly, but the actual schedule and total costs remain unchanged because there is surplus night staffing. To address the cost concerns, we introduced part-time firefighters as an alternative staffing strategy. The model shows that relying more on part-time workers significantly reduces the weekly labor cost to about $113,280. Staffing needs are met using 96 part-time day workers and then 112 part-time night workers. This solution eliminates the benefit expenses and avoids overscheduling. However, from an operational perspective, this approach may create challenges related to the workforce experience, coordination, and service quality. In this slide, we examine how increasing percentage of part-time staffing affects labor costs. When part-time usage is 10%, the total cost is about $284,990. At 20%, the cost decreases to $265,070. At 30%, the cost further falls down to $247,142. And when it reaches 40%, the cost significantly declines to $227,222. Increasing reliance on part-time staffing reduces the total personnel cost by lowering expenses, improving scheduling efficiency. However, managers must still balance the saving with potential operational considerations such as workforce experience and service reliability. In Part E, we evaluated a proposed scheduling policy where firefighters work 60-hour continuous shift per week. The results show that the total cost increased to $158,323, which is about $1,277 higher than the base cost. This schedule provides some advantages. It reduced the number of weekly shift transitions, creates a more compressed work pattern, and allows a longer continuous assignment. The disadvantages are that the higher total costs and the longer continuous working hour may lead to fatigue, reduced alertness, and potential safety risks, which would affect emergency response performance. Therefore, although this schedule may appear operationally convenient, it's not the most effective overall solution. In Part F, the model evaluates flexible scheduling options under 60-hour weekly limit and over 30-hour benefit eligibility. The 5-day schedule has the highest weekly cost at about $159,600, which is $2,554 more than the base cost, but requires only 44 firefighters. In contrast, the 1-day and 2-day schedules have the lowest cost, about $113,280, which is $43,000 lower than the base model. They require 208 and 104 firefighters, making them very difficult to manage. The 3-day schedule provides the best balance, lowering the weekly cost to $152,258 while keeping staffing manageable at 70 firefighters. This slide presents a detailed example of the one consecutive day schedule. Under this structure, the total weekly shift hours equal to 1,154 hours for day shifts and 1,344 hours for the night shifts, resulting in a total cost of $113,280 and a workforce of 208 firefighters.
Looking at the data generated by our model, the optimized staffing schedule meets all the firefighter requirements for both day and night shifts. The model identified the lowest cost staffing plan at $113,000 per week, which is significantly lower than the base cost of $157,000. The pie chart shows the distribution of shifts, where about 60.6% are full-time shifts and 39.4% are part-time shifts. This balance allows for the department to maintain reliability while also controlling labor costs. The bar chart highlights the difference between the base cost, the optimized model, and the resulting savings, showing how the optimized staffing plan significantly reduces overall labor expenses. Next is the analysis behind these results. Using Excel Solver, we developed an optimization model that determines the minimum cost staffing schedule while still meeting all firefighter staffing requirements. Under the original base staffing structure, the weekly cost came out to $157,046,000. However, once Solver evaluated different staffing combinations, it determined that incorporating part-time staffing significantly reduced overall cost, lowering the weekly staffing cost to $113,280. Our scenario testing also showed that relying too heavily on full-time firefighters increases total labor costs, since full-time staffing tends to be more expensive and less flexible. Overall, the model demonstrates that the most cost-efficient schedule balances both full-time and part-time shifts while maintaining full shift coverage. In conclusion, our Excel Solver model successfully identified a staffing strategy that meets all operational requirements while minimizing the labor cost. The optimized solution reduces weekly staffing expenses from $157,000 to $113,000, representing a significant improvement in cost efficiency. These results show that incorporating part-time staffing strategically can improve financial efficiency without violating staffing constraints. Overall, this project highlights how optimization models can support better workforce scheduling decisions through data-driven analysis. That concludes our presentation. Thank you for taking the time to watch and listen to our analysis, and we appreciate your attention.